Oh, and now we are recording. It is 8:45 on Friday, June 28th. This is the end of week number 2. This is C290, A590, Introduction to Quantum Advantage. As I said before, if I'm here all by myself, there's nobody in the Zoom, I will pretend I'm on TV, no audience, and no audience in front of me, and I am just doing some sort of podcast or whatever. So that's great. I'm sure that people will show up later. Example, right now I have Christian joining us. That's it. So there's Elma coming in too. And we have all of us 2 people. There's Alisa coming in. And there you go. Okay, now that we have for people. I started recording a little bit earlier when I was all by myself in Zoom as well as in class in the classroom. But now we have Elmar in the classroom and 2 people online, Alisa and Christian. So I guess it would be fair to let's talk to both of them. How are you, Christian? Can you say something?
I'm all right.
Okay.
A little groggy, but I'm all right.
You are all right. What was that again?
Groggy.
Groggy. Okay.
Yeah, like tired a bit.
Tired because of the relatively early in the morning, right?
Yeah, just a bit.
That's I totally understand. And then how about let's talk to Alisa. Alisa, how are you?
Doing all right.
Oh, excellent, wonderful. So then people online can hear us and we have Blake joining us. So I think other people will come and that's what we find. Okay. All right. Great, so now I'm gonna tell you that today, once again, it's Friday, June the 28th, and I am here, and I'm also online through connections, and then currently synchronously at the same time with all of us. We have Elmar in the room, and then I have Alisa, and then I have Christian. And then we have Blake in the Zoom, and that's totally great. So being the last lecture on week number 2, it would be good to make sure that everything we wanted to do has in fact been done. And at the same time to try to describe, I guess, review, make sure that at the end of week number 2, we have enough information to claim week 1 and week 2. I did get power last night, and as a result, I saw your email. That's a really good, thoughtful share that you proposed. So Elmar sent me links to the documentation from Qiskit, and that's great. And I'm going to post it. I will not be able to. I really still maintain. So if you close this and then you go to the class, which we should start now. I'm not sure if I'm going to get the website. No, I'm not. So I'm going to have to type the whole thing. If you look at it, I say that there's a what's new, which simply says, oh, I got something for you guys, because I came here last night to do the lecture for today. And I did. Then I posted something. But let's see, what was I going to point out? I was pointing out that the office hours are indicating that I was waiting for the power to be restored at home. And Wednesday was no power, and then Tuesday, as soon as we finished the appointments, luckily we did have the appointments, then the storm started, and then immediately everything went berserk. And so I'm looking at this, and I say that if we spoke briefly to Alisa and Christian, we heard their voices, they can hear us, and I suspect everybody else can hear us. If you have any questions or need anything, you can speak up, or you can send a message in the chat, and I will see you. And it is the case that oftentimes I actually respond to that in about 2 to 3 minutes after you post it. But once again, if you want immediate response, you just speak up, and we will hear you, and that's going to be fine. So what's happening today is that I do have some meetings in the not morning, but around 1 o'clock. Therefore, I'm not going to post anything about Friday. I will resume office hours on Saturday and Sunday all day long. But I will not have actual meetings that we normally schedule, just because of the power outage that has destroyed some of our regular schedule. But I'd like to prepare for a set schedule of meetings for week 3, 4, 5, and 6 because the first set of meetings actually went very well and people kind of know now what they want to do. So having said this, I'm going to update this and I'm going to go to what's new. So when you look at what's new, I guess back to where we made a plan for the entire week. Since we are going back to describe what we thought we should be doing, I want to verify briefly that we have in fact done that. So we started with probabilities in Python, and we said you can solve them in the mathematical sense. And eventually we did write LaTeX actual math in Colab. We indicated Colab is going to be our environment of choice. We created GitHub repositories, and most of you have submitted those notebooks. We set up Qiskit very simply in the sense that we had, by the end of first week, a circuit that was in fact made out of quantum gates, that only 1 qubit quantum gates. We have Carla joining us, that's also great. I asked everybody to watch Terry's video. The main goal of that video was to actually describe superposition coming out of the peak box. He calls it peak, but it's Hadamard. We talked about superposition, therefore. We talked about phase, which shows up in our case as a minus. Phase is a type of rotation, but we just go with no rotation or rotation not full circle, but half circle. Interference, and that's the purpose of phase, to actually produce kind of like antimatter, so to speak. Not really, but it's a qubit with a different phase then interferes with a qubit that has the opposite phase in a destructive sense. It also interferes with a qubit that has the same phase in a constructive sense. We talked about X, Z, and H. We discussed that gates are being provided in the Misty state formalism as a set of axioms. I told you that the axioms represent the columns of the matrices that the actual gates have. And then we proved some simple properties. One of those properties that we described, I don't know what page is on the little qubit set, it was essentially the fact that we have two bases that we become aware of, 0 and 1, that's called a computational basis, and plus and minus. Plus and minus come out of H from 0 and 1, and that's called a sign basis. And then it turns out that what X, the NOT gate, does for 0 and 1, Z does for plus and minus. We introduced Andrew Helwer's video, and I have actual evidence that some people have watched that, and they appreciate what he says and how he says. He does talk about in mathematical conventional sense, and as we discussed the first week, I emphasized that there are 4 resources that you have to work with. You give priority to Terry's book and then qubitset, because that describes what I'm going to show you in class. But then the goal always is for us to connect with the mathematics that you have in the Martin Laforest book, Lafore or Laforest. I have talked to him and clarify exactly what's the big deal about the name, because John Donahue calls him Lafore, which would be a French thing, but then he writes it as Laforest, which I don't know. Anyway, that's Martin, and he wrote
French. You don't say.
I think he's French, but it's not Lafore with the accent. It's Forest. So then still Donahue calls him Lafore. So I will have to ask him, how do you want your name to be? And it may be a superposition. Half the time you say Laforest, and half the time you say Lafore in a random way.
I think, yeah.
Who knows?
Yeah.
That's the unit circle state machine that I want to talk about today, because I posted some questions and I also posted some challenges at the beginning of the week, but I also have some questions for you at the end of this week that I will ask in the interviews that we do next week. Remember, John Waters is coming also from Waterloo, but he has I will not show it to you right now because I think I have it somewhere. He has a long, about 9 videos that he posted over a 1.5 years, and he keeps doing those for beginners. And although they are very thorough, so it's not going to be boring, they are really for beginners, but they're very clear. Tommy Wong textbook is the one that we really should relate to it by the end of the semester, 6 weeks in summer now. You say, I start with Misty states and the qubitset thing, the guide gives you a lot of examples. Those are the examples that I will find later in Tommy Wong's book, which doesn't use Misty state. We're going to have to go through Martin's book to get to the math over there. He has a gain qubit touchdown, which is really in some sense our little diagram with more transitions. I basically said that we are going to talk about Mathematica. That's true. Maybe today we're going to do some more from Alpha. And there was a lecture by John McNally, which we experienced. We also set up the first set of interviews, and they went very well, except they started on Friday, and then it ended on Tuesday, and then the storm came. So these are things that he said he will discuss in the lecture, which he actually did. I said that for people who take this class, we meet 6 times, and then I make sure that I give you the credit on each one, because the goal is for you to tell me what you've learned, and for me to try to correct that if something doesn't sound right. And in the process, if you realize that what you said, if there is a mistake, and you realize what I say is in fact a real thing and you understand it, then you get a credit. So you take average of those 6, and we move on. The second week says we need to discuss more support from systems, in this case NumPy, and related to what Mathematica showed us or what we can get through Wolfram Alpha. There is a book that we have to have reading assignments from very soon. I posted that as a list of resources. That's where he says the subtitle is what a little mathematics can do for you. In fact, now maybe I can get to it. I got on class notes, and if I say resources, this is the book by Bird. People who can log in, but everybody else can go into Canvas, and this one here is the book by Barry Bird, right? Suter is also there. He has 2 books. One is Dancing with Qubits, and the other one is Dancing with Python. So the Dancing with Python says if you don't know enough Python, then you can actually follow my book. Now we do have 10 teachers, and they range from middle school to high school. That's I'm going to say maybe 6 classes. Question is, what exactly can we teach those students? And I think that between the 2 books by Suter, basically cover all the entire spectrum. If you just want to show them Python, that's not bad, and that's how we study with probabilities. Well, that Dancing with Python is available. I did put it in Canvas. It's not here. I did put it in Canvas. So and we have to keep graduating to more advanced elements of the quantum circuits, and we have C0 swap and control Z. We discussed phase kickback, and we had our first setback in the sense that I came up with a new method that I thought was clever, and then that confused me the day after. We left the video unposted until we got into class to discuss that derivation, and then we fixed it. Everything was great. We have 2 ways of doing phase kickback. And then we discussed the first case of quantum advantage. That's Bernstein-Vazirani. I have to give you a link to a book that was published in 2019, National Academies of Science, where they were saying, what's the status of quantum computing? That's 2019. And there is very clear-cut descriptions of what the Church-Turing thesis is, the extended one, and how Bernstein-Vazirani breaks it. I want you to realize that in this class, you're going to look at simple examples, scale down, just 2 qubits in the input. And that's going to be true of all the other algorithms. And so you get the scale down version of the big things, but we do the scale down version. Once you understand everything, then you can actually graduate to generalized examples of this. So I would at some point ask, probably not this week or the week after, maybe the week after, I'm going to say, well, can you give me a description of Bernstein-Vazirani in our resources that actually is consistent with what we showed you, but acknowledges the fact that what we showed you is a simplification so you can see the actual specific advantage. So what was the advantage? We had a box full of control knots, and you saw it, that if I do the connections one way or the other, one of the problems is very easy. But the other one, in the classical sense, is hard. But phase kickback allows me to switch the hard problem into an easy problem the way I used to do with the other connections. And so that's what we did last time, because the key was use Hadamard gates. Why would I do that? So you could apply pluses on the controls and see them change by the wire at the bottom. We didn't do any matrices in Python. That's part of Bird. Although we did matrices, and I showed you the diagnostic quiz from Berkeley, and that's part of the deliverables for this particular week. Linear algebra, Jacques Floor and Martin Laforêt, we did bring it up. You won't have to solve those problems, but it's always important for you to realize that I posted questions that I think look intimidating, that absolutely all have answers in that document. So you can say, oh man, how scared am I? Because I haven't done matrices in a long time. But then go back into the document by Martin and you will find all the answers. Everything explained. It's nothing new. The quiz is one of the deliverables, as I said, and today I'm going to go through it to show you what I have to verify that the thing that I posted is in fact the thing that you can put together in 15, 30 minutes and then review it and then post it. And we described entanglement. Well, did we? We did not. This is what we are going to do today. Bell states are a type of entanglement between two qubits. GAC states are a type of entanglement between three qubits. The time evolution of a quantum system with multi-state formalism is something that we have done already. If I have a circuit, I go left to right, and I show you, if I slice it, what's happening with the combined state of the circuit. We implemented Bernstein-Vazirani in Qiskit yesterday, and I showed you that with the only exception of the fact that Qiskit reports things in backwards, I mean the order of the qubits is different, then what we know is what's happening. There is another book which I haven't shared with you, but if you want, says the other Wong book. Well, I tell you, this is a crazy book in the sense that it's so exciting. The guy is so happy to have written the book that he rewrote it and added videos. And now I'm going to show you what it is. I will actually absolutely post it. This guy's from San Diego State. So 2 now. Yeah, 2 is that's good. And I'm going to go to resources, and I'm going to come here, and I think his first book is From Zero to Hero, I think. Where is first, this is right up here. Where are you? Well, I don't see it, but I will find it in a second. This is the Mathematica book, and this is his book. So this book that you're looking at right now is the first version. From Zero to Hero, that's from layperson to a programmer in 30 steps. This is an excellent book, the first version, and I'm not sure the second edition. I have it at home. I'll post it tonight, I promise, in Canvas, along with Mike and Ike and Riefel and Pollack and so on. So I'm having 4 or 5 more resources to be posted. The benefit of this book, this is the one without videos. He wrote this in 2022, but then he rewrote it, and in the new version. He has a video associated with almost every section. So you can go online and watch the video about that particular section. The good thing is that the sections are small, which means that you can start reading and take breaks frequently to understand what's happening. Everything is in here. And you will see his style is really great. It's also very well structured, and it tells you, this is what I'm going to teach you. At the end, verify that I did. So that's the other one book, and I really like it very much. We should have the second of 6 weekly exit interviews, but we won't because of the storm. But we are going to start next week, and maybe, I don't know, if I do it every other week, that's totally fine. And then with a thing at the end, or maybe we just keep doing it. I only skipped week number 2, and then we are going to have 2 interviews in 1 week, and then everything will be 6 interviews. All right, so what is next week? What you see is Deutsch, Yoja, and Grover. These are algorithms that are well known, established examples of quantum advantage. Helwer talks about Deutsch Yoja. None of them is using entanglement, which is totally fine. You will switch to complex numbers in Martin Laforêt, and we should discuss what exactly, how could you possibly imagine a controlled Hadamard gate? Would you possibly think about it? And if so, do you know how to compute with it? And it will turn out that after doing Grover, after doing Deutsch Yoja, and actually doing, for example, superdense coding, which is a way of transmitting 2 bits with 1 qubit, then you say, wow, multi-state formally does a lot of things for me. Yes, it does. Except that it is a very carefully curved simplification. It's a simplification in the sense that, I don't know, rationals are basically a good approximation of the reals. Because what's missing is the rationals, and you could say every irrational is a limit of a sequence of rationals. So in the theoretical sense, you don't need to learn anything else. But in an engineering sense, you need everything that you could possibly get your hands on. And as a result, we need to ask ourselves if the Missy State formalism produces either very long, clumsy descriptions that are accurate or fails when the descriptions are simplified, then is there any way we can actually improve this Missy State formalism? And the answer is absolutely. Carry the probability amplitudes in the description of a Missy State formalism, and as a result, you almost get to the point where you can do direct algebra. Great, because then slowly, we are going to use a regular conventional mathematics towards the end of the semester. So that also shows up with the W entangled states. And then the S gate finally becomes available to us because the S gate wants to use I, which we cannot do at this point. And then you get the interesting properties. What is the square root of naught? What I'm going to ask Elmar, what do you think is, I have a gate, naught. What is the square root of the gate? What do you think? That sounds strange, sounds interesting, or is nonsense? What would you
It's
say?
not nonsense.
It's not nonsense, okay?
No.
But can you prove what you just said? What's the square root of a gate?
What?
The answer is not a number, of course. The answer is a gate, which in sequence with itself produces naught. So can I split naught into gates? If I can, then that gate is a square root of naught, because it's going to be square root of naught followed by square root of naught. That's basically naught. So we will have interesting properties where the Z gate is the square root of S, or the other way around. You can look into the qubit set as a section that's exactly entitled that way. So then you get, oh, okay, everybody talks about that. I need to understand. When I first, a long time ago, I heard about the square root of naught from David Deutsch, I just thought, oh, that's crazy. What is that? How do you take the square root of a gate? But it simply says that if you put two gates next to each other, it's almost like you multiply them, because you multiply the matrices. And so that construction is, if that construction, two gates are identical next to each other, give you the NOT gate, then the gates that you put in there are the square root of NOT. That's a very simple concept, but you could in principle come with your intuition and say, oh, it doesn't make sense, or it looks weird. I think I'm finished with the description, you know what to expect. And now I'm going to come to 28. Today is 28, and look what I have. I said I have two notebooks that I prepare for you. One creates a Bell state, the other one creates a GAZ state. I need them both. I need a GAZ state to show you something somewhat better than the CHSH game, which is what John showed us. But that requires things to happen so I can say statistically 85% of the time I win the game, which is classically impossible. Therefore, I'm using the quantum realm to do that. And then the Bell state is fundamental, because otherwise I wouldn't have any kind of communication. I couldn't do quantum teleportation. I couldn't do superdense coding. So superdense coding has entanglement and is completely describable with the Missy state formalism without any extension whatsoever. And now, if I see you next week, I guess I'm going to ask the following questions to you. What is a Bell state? As I said before, I need to make these challenges because you should be challenged. But at the same time, any challenge that I issue to you is a challenge that you can issue back to me. And if I explain it to you and you seem to understand it, I'll give you the credit. What is a GAZ state? What's superposition? What's phase? What's interference? How many types of interference we have? What's phase kickback? What's the block sphere? What's the bursting Vazirani algorithm? What's the Deutsch-Joja algorithm? I didn't put Grover over here, but by the end of next week, it will show up. What one qubit gates do you know? You know fewer than you should because, for example, S is not accessible to you right now. Do you know where to find the matrices? And at some point, you should say, can I confirm some calculation that I do with the Missy state formalism using the matrices of the gates? What two qubit gates do you know? What are the matrices? Can you translate these Missy states in conventional states? And can you add in the same picture the transitions for the Z gate? This is something I issued on Monday. What was the most challenging part of the diagnostic quiz in your opinion? And I would be interested to see that. So now, again, unless somebody has any question, I'm going to stop sharing and I'm going to go to the iPad. And I'm going to describe the first thing that I'm going to say, okay, and click this, and I'm going to go into Zoom. Where is the Zoom? And I'm going to start sharing the content. I'll share the screen, and I hope it's going to show here. And I say start the broadcast and I go out of this and I'm going to. I don't want to share the device, right? Of course not. I hope that you guys are still hearing me and that's something that we did yesterday. So I could basically I can do this, right? Sorry. And then I can move it here if I want it. I don't want to. So I'm just going to come back to this. Say what is this? We talked about entangled states. So my question earlier was, did I describe entangled states? And the answer is yes, we did, but not a lot. So I wonder if you can still hear me. Let me please ask Carla. Carla, can you talk? Can you say yes or no? I mean, just say yes if you can hear me and don't say anything otherwise. Did I lose the audio with you, with everybody?
I think we can still hear you.
Oh, thank you very much, Christian. So let me do this. Where's my pen? Okay, right here. I'm going to say to you the following. Okay. One of the challenges that I have issued as a summary to you is eraser. I'm going to erase all of this. So there's me erasing right now, and hopefully that thing is good. I'm going to draw that circle, which represents the unit circle transition state machine from Andrew Miller. And then I'm going to do the first things that I've done. Come on, I clicked on the thing, but the pencil doesn't want to. And okay, there you go. So here's the circle, folks. This here is the circle that represents the state machine. And now I'm going to say that if this is the circle that sort of has that thing, I'm going to put something here. I'm going to put something here. I'm going to put something here, also here. And I believe that I have two of them there. Like, yeah, let me see how many I have. So overall, do I have 4 plus 4, 8, or do I have more than that? I have 4 more. So I got one here, and then one here, and then one here. This is a circle that we were talking about earlier. I'm going to come back here and I'm going to say, what do you guys think about this? Does it bother you? It does bother me a little bit. Sorry about that. And I'm going to connect it like this. Great. Now the question is, what is in these places? So I'm going to say that I have a diagram that is in the little qubits and I'm looking at it because for some reason I probably can take the I suspect I can take the picture and paste it here and then draw on top of it, but instead I'm just going to recreate it. And there's a little bit of inefficiency, I suppose, in what I'm doing. What exactly do I have over here at the very top? And I think that we discussed that this is going to be that. So you can look into the qubits, and now that's the state at the very top. And if I see something, I do something that is bad, please let me know. This is clearly equal to 1. And this is the same thing as saying 0 times 0 plus 1 times 1. And so the original thing was, can you please write down the states that we have to, that we have on the circle, but in conventional sense. So then, all right, we have a white here, which is essentially the same thing as one outcome inside the curly brace. It's a superposition of only one state. That basically is the classical bit. So this is going to be 0, like so. And if I want, I'm going to say probability amplitude 1 for 0. That means when I measure, it's going to be automatically 100% 0. And then there's a 0 chance of getting a 1. And I'm writing this down. And there you go. That's my qubit on the right. I have, as I said, 4 plus 4, that's 8. I've done 2, I have 6 more. So I guess I'm going to go next to the ones that I like the most. For example, here, I have this. And I guess I could ask now anybody, how do you describe this? And let's pretend we have no idea what we are doing here and we've never done this, but we know the actual information. We know the way it should be calculated, thought about, and so on. But we haven't done this before. So then under this, you say, open the Jews for quantum on page 83, and then look at the way they calculate the probabilities. Then you know that it's going to be some 0, and then a plus. I don't see a minus, right? And then multiply by 1. This is the thing that we are looking at. But what are the probabilities? Oh, calculate, and then you say 1/2. If each probability is 1/2, then in the formula, you have to put the square root of that. Those are the probability amplitudes. So here's how I reconstruct the actual conventional description of the qubit. 1/square root of 2, 0 plus 1/square root of 2 of 1. Square each one of these probability amplitudes, add them up, you get to 1. There you go. This is actually very, very well known as plus. And that's why you have, for example, a transition from where? Oh, you don't have all the transitions here in the circle. You only have some transitions. For example, I would have peak is, oh no, I do have it. So inside in the actual circle, I have this thing. It's a blue arrow, goes both ways. And who makes this transition? H. And that's going to be the peak box or the Hadamard gate. Okay, do you have anything against this? I can say, for example, out. I said blue, right? Okay, then here's blue for you. And that's going to be exactly as in the diagram that we have inside the qubit set on page 11. This is basically a peak box transition or a Hadamard gate. So clearly from 0, I can go to plus, and from plus, I can go back to 0. And that's how we know very, very well. I'm not going to do more, okay? You are going to say, for example, there is another transition, and I'm going to do it with red, because that's how it appears in the diagram that you have in the little qubit set on page 11, which is Andrew Hilbert's diagram, but converted into Misty state formalism. Who do you think is responsible for this transition that should actually be straight line? So out, you are a straight line. Yes, you are red, but who is responsible for this transition? And the answer is not gate. So I can put an X on it. Of course, if I start with the black and I put an X, I come up white, and then I do X again, it goes back to black. That's what we discussed in the very beginning. Now, these transitions, I'm going to erase them at some point because I don't care for them. On the other hand, you know, I could do this later and say, I got more stuff to write, so yes, I will. Okay, but now let me just go back to where we were, the size and so on. All right, so then if you understand what I'm doing over here, seriously, that's what you should be doing if we were to ask you during class interview, and you say, sure, I'll do this, whatever, it's not hard, because you would practice first, or you would come for office hours if you don't quite know how to do it. I'll show you, and then like I'll show you right now, and then you come and say, now I know everything, so I can just show off. So then I'm going to come back to black, and I'm going to say, what exactly do I have elsewhere? For example, here I have a white with a face on top of it. Well, this is going to be clearly the same thing with this thing, but now you're going to ask yourself, I don't have a 1. That's true, there is no 1. So can I simplify this? Of course, what's the probability of getting a white? It's going to be 1. But in the formula, you're going to have minus getting a 0. Okay, so that's minus 0. So you say the probability of getting a 1 is 0. What's the probability of getting a 0? 1. But I have a phase, and the phase doesn't show up in the measurement. If I measure, it's coming up 0. But the formula is with a minus. And you say, wait a minute, can I calculate the probability the way you taught me? Sure, take -1, square it. That's the probability of getting a 0. It's 1. Because -1 times -1 is 1. So that's the formula over here, and it's just a matter of phase inside of the formula. There's 0, 1 in there, and we finish with that exercise. So I'm going to come back over here, and I say there is at the bottom of this diagram a block with a face. Clearly, this is the same thing as -1. So this is the same as -1. The bit that we know as 1, which is represented as a circle that has black inside, is basically there with a minus in front of it. And now I'm going to go here, and I'm going to say that this is a Misty state that has white and then black with a phase on top. So what do? You say, well, there is a 2 outcomes, and each one has a probability of a half. We did discuss this earlier, basically here. So the probability is 1/2. That means I'm going to say 1 over square root 2 of 0 minus 1 over square root 2 of 1. It's good to convert between these formalisms, and that's what we are practicing right now. It's not that hard. If you look at it, like Elmar was telling me earlier, when I see this, he said, I am going to assume that I get 1 in 3 chances of getting a white. Oh, I thought so too, but that's not the case. And Terry explains on page 83, this is a rule that you have to remember. That's the correct rule. Just like we discussed, you know how the Hadamard gate should do a minus on whatever, because it looks good to me. Yeah, but that's not what the nature does. I mean, go ahead and define that and see if it takes you anywhere that everybody else would benefit from. But if it doesn't, or if you don't have the time, no problem, because that's not how things work. So likewise here, this formalism here indicates that you get 1 squared over 3 squared, n squared over n plus squared over n squared. So it's going to be, this one here is going to be 1 over square root of 3, 0, plus, what do we have in there? It's going to be 4 over 9. And that's going to be, now I am messing it up. So then white is going to, I'm going to have to do this again. Oh, absurd. Yeah, it kind of looks the same as you said in the beginning, but that's a little bit disturbing. So is equal to, I have a 0, and then I have a plus. And the question is, how many ones do I have? So I'm going to say 1 over 1 plus 4, that's 5. We discussed this before. So the idea would be that is if this is n, come on, pencil. If this is n, and this one here is m times, then I'm going to go and say n squared over n squared plus m squared, which in this case is going to be 1 over 1 plus 4. That's 1 over 5. So 1 over square root of 5, that's the probability. Definitely not 1/3. Oh, can you make a mistake and actually even calculate 1/3? I just did that, but that wasn't bad. That wasn't good. So then what do I have over here? I almost can tell it's going to be a square root of 5 here. Except though, instead of 1, I'm going to have a 4, which is going to produce a 2 when I take the square root. Is it true that 1 over square root of 5 squared plus 2 over square root of 5 squared gives me 1? Yes, because it's going to be 1 plus 4 over 5. Okay, so that's an example of how you calculate the probabilities in general and how you convert to probability amplitudes. And this I could just erase because it's just an example of how I do things. And it's basically how I'm calculating these other formulas. So my last 2 examples is going to be here, white with a face and black. Well, what's that's going to be? I think I have a 0 over here, and then I have a plus, something about 1. But the probabilities are in fact exactly as before. So this is going to be 1 squared 2, and then this is going to be with a face, so minus 1 over squared 2. That's that one. And then I have 2 negative things over here. So I'm going to say this part is like so. And I'm going to say that what this gives you is not just a conversion. It's good to know 2 languages and convert from one language to the other, speak to people who are from different countries and stuff like that in real life. And in this case, that gives you exactly that, but it gives you even more. So it's not that I switch from one language to another, but now the operation in that language is different. So here I could say, if I do this, and I can immediately tell you that this is 1 square root of 2, 0 minus 1 over square root 2 of 1. Now I could do transitions between these states using matrices if I want. And then you say, okay, so in this new world where they look different, and when I have the time evolution actually given by unitary matrices, which I then look up because I'm in the process of looking at Martin LaForest's linear algebra chapter for young students, then I guess I can actually reproduce the result that I do with Missy states, and I can get more confident in Missy states or more confident in the other one. And so these are the conversions. Now, what I'm going to do is I'm going to say, make this slightly smaller. Any questions, I can easily take them now. But what I asked you in the second part I said, would you please be able to tell me what Z does in here? So I'm just going to say, what is Z of the top, which is just black? Oh, that's a minus. I'm sorry, I got too many minuses. Yeah, so forget the minus actually. Put a thing at the very top. So Z's purpose is to put a face on one. And what that means is that at this point, if you start on in this one here in this stage, then Z will take you here. That's what Z does. But we have only proved this part. The truth is that if I do Z of black with a face, that's going to be first. What do I do? I'm going to take the phase out, and I'm going to say this is a phase applied to Z to black. We discussed this, and we have two operators, and we can just choose whichever we want. And so I'm going to say this is that. But we discussed that two phases on top of each other are going to give me the number and so on. So there you go. This guy is both ways. So I said, could you put Z to do the transitions between these states? Oh, there you go. I converted those. What about Z applied to white? This is going to be, we discussed it before, the identity for this particular input, which means that Z here is going to give me this. That's Z. So we had for not, I think we had this thing for not, right? So not or X, okay, is going to take that state and give it back to you. Z takes white and gives it back to you. So here I could just erase these things because I should have come up with the specific colors. But I'm going to keep the black transitions of Z. Great. Now, what do you think happens when you do Z of this guy? That's going to be Z of white with a face on top, and that's going to be that. Haha, that means that Z stays here. This is Z. So Z stays in the white with a face, and Z converts between black and black with a face. Now, I don't have any other pure states here. The only states that I have are basically superposition. So I take one, for example, Z applied to this one. That's very simple because Z is going to be an operator and the superposition operator is another operator. So what I'm going to do is I'm going to switch the superposition operator with Z. So I have Z applied to this guy and Z applied to black. This is Z applied to black. And what you are going to see at this point is going to be white followed by black with the face. And that means that Z takes me from plus, which is right here, and moves me into in here. So Z converts between that one and this one. Okay, so then I'm going to say, well, what happens if I start into the outcome? Will it take me back? And the answer is it has to, because Z, X, H, all these matrices are basically reverse versions of them, inverses of themselves. So if I apply this to, and you will verify this on your own, and then you say, oh, now I believe that that is the case because it always gave me that. And if it doesn't, then you say, oh, I made mistakes in my calculation. So it's going to be Z applied to white, and then Z applied to this guy, which automatically, if you allow me to just skip some steps, I'm going to say that white stays white, and the black becomes black. And black with a knot is going to have the opposite of black with face, and that's going to be two faces are going to cancel each other. Therefore, that means I'm going to go in between these. Also, this is Z. So, so we have this thing over here, we have this one over here, we have this one that we just described, and I have this one. So I guess it's going to be, let me just use green. I believe, okay, that's not what I meant, but I'll come back over here. I'm gonna say, I believe that there's one last transition, and that's this one. That's what I believe. So I would like to prove it, and then I'm gonna go back to the desktop, switch from here to the desktop to show you the entanglement as well as the diagnostic quiz, and that's going to be the end of the lecture today. So I'm going to apply, I'll write in green now. So C is going to be applied to this state, which has a white with a face and a black, which is now green. So then, all right, it is green, but I'm going to go back to black. Okay, for the last transition, I'm going to apply Z to white followed by a with the face and the blue thing. Okay, so what does that give me? It's going to be a superposition of z of white with the face in here, comma z black. And you say that look, if the face is in fact inside, oh yeah, let's do this, I guess. Let me write it again. This is z where the white is being inside. Then carefully take the face out and then apply z to white. That leaves the white unchanged, but the face is there, which means that I'm going to get white with a face here, and then the z applied to black is going to be black with a face. Okay, and so at this point, as we start playing the game that of converting stuff, and you know which language the people in general speak, maybe you could consider that it's a good way to start with misty states, and then it's probably a good thing to try to convert and switch to the real language that everybody speaks. So that's the thing that we were trying to do here, and this is the reason why we take this approach. I honestly generally believe that it's easier and more fun to actually work with the misty state. It doesn't give you any corners being cut, but it's somewhat easier. Maybe you can challenge that and tell me why it's not. But in the end, we really want to take you to the conventional mathematics, and there's nothing wrong with that either. So you can see that from the face white superposition with black, Z is taking you to face white, face black in superposition. That means that I can just apply Z to that state to see if it takes me back to where I came from. And once again, that's one property of these matrices. Z is in fact a matrix. If I apply Z of Z, that's an identity. If I apply X of X, it's an identity. If I apply H on H, that's an identity. And so on.
Square.
If I Z times Z is 1. It's a little bit strange, isn't it, that you say Z is square root of 1? That's not true. But if you apply one of these gates again to the result of itself, it takes you back to where you came from.
Yes, but you said that is Deutsch. Miss Deutsch have said that you can take the square root of gate.
You
It's
can
not
take the
same.
square root of naught. You
It
could
is
take.
not, it is not the same. No, it's not.
So once again, look at this.
Stupid question.
You know what naught square root of naught is? It's going to be some matrix which multiplied by itself is going to give me naught. So let me just do this. Okay, where's the eraser? So square root of naught is something, okay? I don't know how to call it. I guess question mark. What is that? Well, this times this is going to give me naught. So I think what you're saying is, then I guess the square root of naught is not a unitary matrix because it would have to be its own inverse. I guess so. So we can come back and describe this.
Yeah.
However, what I said is that all these matrices, Z, X, H, if you multiply them by themselves, then you get the identity matrix. So what if I said something that's wrong? Can we verify that what I said is actually partially correct or not? So what I keep saying over here is that if you take a state and you apply Z to it, you are taken in another state. And if you apply Z again, you're coming back. That was the idea. So I think I think that we have a good question here by Elmar. So what is the deal with square root of naught? Is it unitary or not? You know, when you say unitary, say whatever that means. But for us, it means at least one thing, that if you take that matrix and multiply it by itself, you get the identity matrix. But this is a good point by Elmar. Since you brought up the square root of naught, can we discuss this later when we get to it? And you say, I don't have the time later, I want to do it right now. Then I guess I'm just going to tell you that page 55 discusses square root of naught and square root of Z. Square root of naught and square root of Z, page 55 in Kubica. Why don't I say here? So Kubica, page 55. And so this is something for us to discuss at some point. What's going on? And then either prove one or the other. Maybe I take the square root of a matrix that's unitary and I don't get a unitary matrix. And maybe sometimes I do, depending on what matrix I'm working with. The thing about this is square root of naught does not have a name other than square root of naught, which makes me think that that matrix is not unitary. However, square root of z has a name. It's S. So sometimes you get a unitary matrix when you take the square root, and sometimes you don't. And now, because we're talking about matrices, we should then switch to that chapter and start discussing what is a unitary matrix? How can you take the square root? When do you get a unitary matrix out of that? Nobody says if you take the square root of a matrix that's unitary, you get a unitary. I didn't say that. All I said is that these matrices that have names, they have the property that being unitary will reverse themselves. So z times z should be the identity. And I think my statement has to be so very clear, crystal clear that we are going to revisit when we talk about what did I say? I said the following, that square root of naught does not have a name, but square root of z is equal to s. Now it is the case, if this formula is correct, the square root of z is equal to s. S is a very well-known matrix and it's unitary. So in this case, the square root of z has a name and the result is a unitary matrix. That's why it has a name. But the square root of naught does not. And we should talk about it when we get to that point. Finally, I'm going to switch back to black and I'm going to say this is the superposition of z face white and z black with a face. So this is going to be phase of z of white followed by phase of z of black. Well, we've done this before. Okay, so I'm going to put an equal sign here and I'm going to say z of white is white, which means that it's going to be white with a face. And then black comes out with a face from z. And there's a face in the beginning. So this is going to be white with a face and black with no face. Did it take me back from this guy? Did I get here? And the answer is yes. So I'm going to erase those two things and I say, that's it. I proved transitions between these states with z. I also converted them, and so I finished the challenge that I issued to you. And that took me a long time, I guess. We had like 15 minutes of a summary, and then we had this problem solved in 2 parts of it, right? And now we're at 9:40, so we have very little left. I'm going to see if I can do one thing before we get started. I'm going to ask Elma, because he's right here in front of me. Elma, do you think that this state is an entangled state or not?
And yeah, yes, it is.
Okay, so he said yes, it is, and he might be wrong, but who cares, right? I think the fact is this: if he's wrong, it's my problem, and if he's right, it's his brilliance.
It's anyway my struggle.
Hang on, exactly. We are going to not be sure, and the problem is that it's like a coin. If you don't say the right thing, you say the wrong thing, even if you wanted to say the right thing, right? And if you said the right thing, lucky as you may have been, so. Is this entangled? I think Elma said, yeah, maybe. Okay, now is this entangled? And I would like to describe an operational test. This is entangled because if I measure one, as you can tell, the outcomes are going to be in sync. Measure the first qubit or the second qubit. I don't know, which one do you want to measure? How about the second one?
Yeah.
You get white, you know the other one is white. If you get black, the other one is black. Now, this is a really difficult thing to say right now with just what we said before. But this is not entangled. Okay, now let me explain to you why it's not entangled. That's the easy part. And then everything that's not entangled is entangled. This is equal to white followed by black, white. Now, you guys understand this, right? Because what would I do if I were to do the product? I would say white, black, white, white. Now, these guys are not entangled because if I measure this, I always get white, by the way. But I don't know what I'm going to get from these guys. Likewise, if that guy gives me a white or a black, and I put a black first, so who cares? The order is not important, but an order is preferred. And I should have put the white if it's preferred. I would have put white first because we do that, but not that it's necessary. So look how they are independent. The second qubit is in a superposition of white and black. I don't know what I'm going to get, but it doesn't affect the first one. So this one is not entangled, but this one is. Why? This one, why is this entangled? Because you cannot factor anything out. You just can't. So example of entangled states. This, as we discussed, this is a Bell state, 2 qubits. This is in fact, okay, is another entangled state.
Can you say, or 2 qubits on all Bell states or only entangled Bell states?
Okay, let me take that question again. What was the again question?
You said now just something is a Bell state, which one?
This one.
Is
2
not
qubits, yeah.
because are Bell states always entangled?
Yeah, that's how we call them. So Bell states are states of 2 qubits that are entangled. The fact that it's Bell means entangled, because that's his major contribution. If you have, he has some inequalities which are basically holds for the classical world, but the moment you use entanglement, you get above them. So entanglement truly gives you something. So the story is with Einstein, Podolsky, and Rosen saying entanglement gives us great inconsistency. And actually they proved stuff about quantum mechanics that they didn't believe in. And then there was a long debate with Bohr and so on. And along came Bell, born in Belfast, and around 65 with his inequalities, and didn't get much recognition. But he said, this was supposed to be. And then people like Alan Aspect and the people in the CHSH inequality and then the GAZ, they said we have to have experiments that prove that Bell's right. And so we should discuss what Bell did and how it changed the world. But Bell states are states of 2 qubits that are entangled. That's the foundation of it. And as far as GAZ says, 3 qubits entangled. And you look at these and they are clearly entangled because there's no way you can separate the behavior of 1 qubit from the other. Or in the case of GAZ, 1 qubit separated from the other 2. Because if you measure in GAZ the first qubit and it's white, you automatically know that the other 2 are also going to be white, because that's how that state is. Great, so now I'm going to try to move this even further. We have this situation, I believe, that if I have an H gate, it takes me into a NOT gate. And we discussed yesterday what happens to this. And then there is, for the GAZ game, I guess you may want to say, well, where is this in the book? No problem, I'll tell you in the booklet. Entanglement is on chapter 6, so qubits are chapter 6, and that's basically, well, you know what the page is, 17. Page 17. Okay, my handwriting is just crazy. And then there are some exercises in there. And so what I just did, a Hadamard that goes on the control of the thing is this is basically Bell state circuit. And then I have another one that says let's do the same thing. This is the Hadamard onto this guy, which has a control knot. And so do you recognize the circuit? It's the same as this one, right? This one is the same, except I'm going to erase that thing. Now, if I say if you do recognize this, understand that the GAZ is using it and says that gives you a GAZ. So this is a Bell state here, and this is a GAZ, and you clearly see that the GAZ circuit uses this, which is the Bell state. So know about these circles, they appear on page 18 of the QBSET. And that means that, okay, handwriting is very bad, but this means that you can essentially practice with this. There are an explanation on page 20. You have an answer of how you should calculate, and then there is a different challenge from a different GAZ. And then it goes into phase kickback. So the idea is we have to define entanglement. What is it? It is something that happens to 2 qubits or 3 qubits. In our case, we keep things small, where at the end of a circuit, the qubits are in such a state that measuring one of them automatically tells you how the others are. Why can we do that? Once again, because the state of the qubits at the end cannot be factored into a behavior for one qubit, a behavior for another qubit. And if you have three qubits, a behavior for a third qubit. If you can factor it out, then that's not an entangled state because then they will act independently in the measurement. But if you cannot factor, then that's the definition of entanglement. So I have a few other examples here on page 17, but just examples. Hey, look at this. Is it entangled or not? And the question in both cases is no. And the answer is why? Because you can factor the behavior of the qubits. Okay, so I'm finished with this, and I'm going to say that from again, if anybody has any questions, that will be perfect. I'm going to get this out and put in Zoom, and I'm going to say stop sharing. Now I'm going to move the iPad and switch to the. I say okay. I don't know what that means. I said okay, but I don't know exactly what I did say okay to. And now I'm going to say share here. And I'm back to what I told you. So here's the Bell state circuit. Let's run this so that you can be sure that what I did is in fact still working. Because otherwise I show you stuff that I've done a year ago, and then Qiski doesn't do that anymore. So it doesn't matter that my notebook a year ago was doing that because it doesn't do it now. But this is done last night. So I always Control Shift H. I always ask to see both the state, or in the case of this one, measure to see the output. The output is 00011, and it's ideally I would have exactly half, but I'm not getting exactly half. This is half of 1024. So you see 508 plus 516 gives you 1024, which is 10 to the 2 to the 10th. But as you can tell, it's because it's completely random, it's not going to be exactly half and half. So this is the Bell state circuit, which has in Qiskit, it gives you the formula, and it also of the state, the actual state. And if you measure, you get basically half and half. And if you measure again, you might get different numbers at 508 and 516. But this is really exactly what we did in probabilities. We either count and produce, or we simulate and then get numbers which are slightly off. And then there was a third version, which is I can describe the solution to a probability problem by writing LaTeX. That in this case is either you use matrices or you use a mixed state formalism. This is Bell state, okay? And then the GAC state is over here. So what I have is essentially another circuit, and I'll rebuild them with you now so you can see that it's working. And what you can say is that the Bell state circuit is right here, and what I do is I'm adding a another control knot. So can I prove that this is producing a 3 qubits entangled, 000 and 111? Yes, of course, and that's good practice for the Mrs. A formalism. And then can I please ask them to tell me what the state is? And then in this case, because they are so symmetric, it doesn't matter that Qiskit, this 0, the first 0 is our last 0, but who cares, right? Because they're all 3 zeros. And that's the I say, well, what if I would like to describe what happens after the first 2 gates? So I still have a wire over here, but this one is a Bell state, and I'm just about to put a control knot. And I say, you know, when I'm doing my thinking, I slice it and I tell you what the whole thing is. You say, for example, let's go to qubits. So I can show you what I'm doing. Then I don't know where it is. So now how about syllabus? Syllabus, I guess. Then you go to C290 quantum, which now it doesn't exist. It's right here. Come on, again. Unbelievable. They only call during lecture. Hello? Hello? Yeah, but I cannot talk before 11. I promised I will call you around 2. I will call you a little bit later today and set this is for June next year, right? The appointment. I'm sorry I didn't call you yesterday because I couldn't, because we had no power and stuff like that, and it was difficult. But today I will call you around noon. Yeah, I have the number and everything. Thank you. Sorry. Bye bye. Okay, just for an appointment next June. Eager to set the appointment. That's great. So I'm coming over here and I say I don't want to do this. I'm going to go into syllabus, and syllabus has a qubit set, and let me click on it. And as we scroll through this, I'm going to remind you, see, this is the part with square root of naught and square root of z. S is the square root of z. So when I go into entanglement, I would say, this is an exercise, do it. This is another exercise, do it. This one says, and that's how you run the circuit, all right? Explain. And then this says, this is how you solve an exercise of this kind. So I'm going to say I have whites in the beginning, and then I have a misty state here, I have whites here. What's happening on these two wires? It's this. But what if I consider all three wires? And this is what I am at this right now in my Qiskit exercise. Will I see 0, 0, 0, and then 1, 1, 0? The answer is no, I should see 0, 0, 0, 0, 1, 1, because it's backwards, okay? But you understand that I'm putting white, let's see, on the third qubit. This is the white here. And I have white, white, black, black that this guy gives me, and I need on the third wire, that's my third for me on paper. This guy here, white, white, comes at the third position. It's Q3, Q2, I'm sorry. And then what's in the red rectangle says, please understand that this white here is the control for this control knot, and this white is also the control for that knot. So then black, white becomes black, black, which you see over here, and white, white stays white, white, because that's how this works. And then the result is white, 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 black, 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 and I don't care about Qiskit or Missy state, they're the same. However, at this stage, I should see the difference. So once again, the Missy state says 0, 0, 0, 1, 1, 0, but this one should say 0, 0, 0, 0, 1, 1. And once again, you could easily get confused, but you shouldn't. And in the process of not getting confused, you get confirmation that the individual slices in through your circuit behave the way you expect them. And that's basically it. So what did I say that I'm going to do for you? It's 9:52 and I'm kind of running out of time. First thing that I said I will be doing is that if you go under to 25th, this should be all of the diagnostic quiz. Okay, now let's verify that. The diagnostic quiz should have how many exercises? 10? 9. I agree with you. So is it true that I have 9 out of this one? Is exercise 1, 2, 3, 4. There's some everybody is not by 3, so we are on 4. Fourth question is still being answered over here. Then you do 5 and 6. Then you say 7 and 8, and where's 9? There's 9 at the end. Okay, great. It has all the exercises, and in the process says, oh, you can reach out in NumPy and do stuff. That's totally great. I am going to tell you one more time that you either understand how I did this or you don't. And if you don't, the good thing is that if you have, I think I did this in class, if you say, what are the eigenvalues and eigenvectors of this particular matrix? Where are they? So which of the following is the eigenvector corresponding to the largest eigenvalue of the above matrix? So I have this matrix and 0, 1, 1, 0, that's the knot, right? So I go to Wolfram Alpha. And last time I said the simplest thing that you can do over here is to ask for the things that they gave you. So eigenvalues of, and I already did this, right? 0, 1, 1, 0. This is the eigenvalues, right? But what if I ask for eigenvectors? So very rarely it confuses itself and doesn't have the answer, but the eigenvectors are going to be negative 1, 1 and 1, 1. So it does, and then if you say, I want to see step-by-step solution, that's not a big deal. It's just that it's intimidating the terminology. But you can, depending whether you are or you are not a subscriber that allows you to see the step-by-step solution, they will provide you the step-by-step solution. So I think that I have the diagnostic quiz listed, and all you would have to do is to copy these into text boxes and then ask yourself, do I understand it? And if not, write it down. Remember, because I have a question, what's the most challenging? You say all of them, or all of them except 1 was good, or all of them except 1 and 5. And just tell me what your opinion is. So now I'm going to go to Google Colab. And I'm going to ask which one of the 2 things that I did would you like to see to be sure that it is working as expected. I'm going to say, give me a new notebook. And I don't think I have time to do them both, so I'm gonna ask Elman, should I do this one, or should I do this other one?
GAC.
I do the GAZ, no, yes,
Whatever you can.
I'd like to do
Fail
this.
state, I would like to fail state.
Yeah, I do the birthday because
Yeah.
in the GAZ, I only did the thing and asked for the
Yeah.
face, and I never did any measurement. But the first one is more complete. So the birthday did last night, okay, so I don't know, 13 hours ago. I start by, and so you should say, I think I know what he wants to do here. Let me see that it works for me. And you would go like this, is a code cell and run it. And it will install the part that tells you what the phase is, not the phase, but the quantum, the wave function is. And then it will install Qiskit to run the circuit and show it to you and so on. So once that is finished, I'm going to import Qiskit. And then I'm going to say that from Qiskit, I want to import everything. So I'm waiting for this. And while I'm waiting, I'm going to say import Qiskit. And here I'm going to say from Qiskit, import start. I put those two together, and if I do run, it says I will run as soon as the first one is finished. The first one is finished, so I'm going to disable the output. And what I have is I got everything that I had to installed, and then I imported Qiskit, and from Qiskit I imported everything that I might be using. So it imports nothing until you use something from Qiskit, and then it takes it, gives it to you, and you can do whatever you want. So I'm going to say this. What do you think? Elma has a nice link, which I will post. It's to the documentation. It's the most up to date, I think, from what I gathered. But these 4 lines are saying, give me a quantum circuit that has 2 qubits and then 2 measurement lines. Now, I will put an H, a Hadamard, on the first one, the one on the top. And then I'm going to put a control X that will have the control on 0 and the target on 1. And then I would like to draw it. So just for the fun of it, if I actually replace this with 1, 0, I don't get the same circuit, right? But I know for sure that the control knot is going to look different. Okay? The control knot is backwards. I'm not saying it's the same thing. I'm just saying that if I were to connect it this way, I get this circuit, which is not what I wanted. But the 2 indices over here, I hope it's not confusing. 0 says either control to that line, and then put the target on 1. And now I have the right circuit. You see the 2 lines of measurements, they are not connected to anything yet. And then I'm coming back over here and I say, please calculate for this whole thing what the state would look. Now you are familiar with what we did. We calculated everything in MISTY states. And then we converted them to regular conventional math. That's what this guy gives you. Not to mention the fact that this is giving you a certain ordering, which in this case is irrelevant because 0, 0, 1, 1, it doesn't matter the ordering. Even though their 0, their first 0 is our second 0. So does this give me the Bell state? The answer is yes, one of the 4. And what now? I will install the part that is able to do measurements or simulate the measurements. In this case, if I'm not connected to a quantum computer, then it's going to do what a computer will do. If you were to be connected, it's a little bit harder, and IBM has changed a bunch of things. You create an account, and then you have a token. People over there in Virginia, they got really upset, and I'll show you in a second why. This summer, they got really upset. I said, IBM, fix this, because you're ruining our summer school. So whether that happened or not, I don't know, but they got really upset. And then I'm very briefly, I have to show you that. So you have to read 2 papers for for Monday. Just look through them and see if they make any sense. At least understand what they are wanting to do, because we are going to solve that with MISTY states. So I say, please measure the first 2 qubits. And then I'm going to say what needs to be done for the calculations to happen. I messed up. I did not install Qiskit here. That's okay. The backend needs to be installed first. And I messed up here by saying, well, give me a code and put this in, but now move it up, move it up, move it up. Do I have it in the right place? I guess just move it up. It's good. Okay, so I'm going to install this part, which without it doesn't work. And this takes a while. And once you do it, everything is fine. Then I will say, run this. You can measure it and you will do stuff until, but only after this thing is finished. So it does. And so I say, first install the backend and then set things up according to what I will show you in what Elmar has posted with the documentation, most recent documentation explains what every line does. And then I come back here, I hope I'm in the right thing, and I say, draw the circuit. I have a problem now, you see, if you are doing things repeatedly, then it just takes the circuit and adds to it. I don't want to measure like this. So I'm gonna have to go and do the circuit again. So here's this part, I run this thing again, you will run into this too. My circuit is as indicated, I did install stuff, do this, and then draw it. And now my circuit is all right. So I have a Bell state circuit with two measurements that will be immediately shown. You will have to calculate, simulate it, run, see what comes out. It's just a regular probability problem at this stage. And it gives you those counts. You get 517 times and it gets 507. And if you were to run it again, you get different numbers. See, 520, 524, 504. So you could even print this as a histogram. It just looks the same because once you have 520, 504, then what you get here is exactly that. And it says, oh, I got it 504, 5. This doesn't add anything, it's just big bars that actually reflect what you just did earlier. So what I would like you to remember here is that for Monday, I would like you to please read these two papers. This paper is an actual paper that Terry Rudolph participated in, and it describes an experiment that is in fact Deutsche Urja, but it's a fun experiment for high school students. And read it and see if you understand what it says. You should be able to handle all the formalism. I think ours is simpler than what they did. They did it 2 years before us anyway. So then you can read the slides from a meeting 2 years ago with the same thing. These are the slides you have to read after you read the first paper. And this is Ed Barnes, and this describes a lot of things. Describes how they set up the school, who attends, what they teach. So it's a follow-up to that paper, explaining how, look, the young students are in fact taking this, and you can tell that that they have to do a bunch of things to connect to the. This is Sophia Economic. And the problem is that at this point things have changed. They got really upset. It was already difficult to connect these students with the actual quantum computer because an adult had to sign for that account. But it was a very successful summer school, and I'm not entirely sure what happened with it this summer on account that IBM changed the entire procedure, which made all their efforts, have to be redone. And if you read these two, then I'm ready for you on Monday to explain Deutsche Urja. These are people who are taking the class. This is Terry with his book, and these are the two people. Sophia, I don't know where Ed Barnes is here. I don't see Ed, but I can show you a picture of Ed later. And that brings us to the end of the second week. No interviews no meetings unless you guys need anything. I would email people and say tonight, no meetings this week, but I'm available for office hours. With this, I'm going to, am I sharing? This is also a problem always for me. I think I'm sharing, right? I'm going to put the video on. Any questions? We need to stop. I guess there are no questions. Then I want to thank you again for your patience. I'm gonna stop recording and then disconnect. And I will get in touch with you by email. Post this in about an hour. I post the links from Elmar as well. And hopefully things will be normal again starting next week. And we're gonna have interviews and all sorts of whatnot. Thank you. I'm going to say stop recording right here. Stop recording.
Thank you.
Yes, I'm